Hello everyone, welcome back to our Calculus 3 course. Today I'm going to continue talking about chapter 15. I'll cover 3 sections, 15.6 all the way to 15.8. It is about triple integrals. But before we get to the detailed triple integral, let me spend a couple of minutes to give you guys a review about double integrals that we learned before, because you guys are going to see the similarity coming out of it to get into triple integrals. Okay, so what we learned before about double integral, you guys see double integral of the function f x y dA over a region, say R for the region. So the first case that we learned was what? And this is, let me draw, this is the x-axis, this is the y-axis, and if you imagine the z-axis is coming out of the board, okay? And the function fxy is like a surface up here. And the region R in the nicest case is going to be in a rectangular shape, where x run from, say, A to B, and y run from C to D. And this double integral can be written this way. Double integral f x y, say dx dy. Dx is the internal integral, so inside one is from A to B, and y run from C to D. You got double integral in terms of x. Okay? And then you can interchange. I will mention what's if both x and y boundaries are constant, you can interchange the boundaries, say dy dx. In that case, and what? The inside integral gonna be from C to D. The outside one gonna be from A to B. And you guys get that already. So in the more general case, more complicated, what if the functions are not that nice anymore? The boundary, the region, not that nice anymore. If y is a function in terms of x, say it looks like this. Any curve, okay? Let's say y2x. This is like y1x, or y is function in terms of x. Okay? In that case, you cannot interchange the boundary anymore. The independent one, the constant, gonna stay outside. The function the variables, the function gonna stay inside. In this case, then you can write as well. Still double integral f x y. This time, dy gonna go first, and then dx go after, and y run from y1 to y2. And again, in here, what we mean is y1 is a function of x, and y2 is also a function of x, and x also run from A to B. Okay. So that region is less nice than the previous one, but it's more general. Okay. And then we have the third case. What if the region that you learn has got a round shape? It's not rectangular anymore. In that case, it turns out that what? We're not going to use rectangular coordinates or Cartesian coordinates, how we say it, anymore. We change to a new coordinates called the polar coordinate. Okay? And we have double integral written this way. F of r cosine theta, r sine theta, r dr d theta, where theta is run from, say, theta 1 to theta 2, depends on particular example, okay? And r run from, say, r1 to r2, and the change formula is what? X is equal to r cosine theta, y is equal to r sine theta, right? And dx dy will be changed to r dr d theta. There's actually a formula called the Jacobian determinant. Let's tell you. And in the end of the video clip today, hopefully, if I remember, I'll give you the formula. It's not covered in our course, okay? It's in, I think it's 15.9. You guys can read it for yourself. But hopefully, at the end of everything, I'm going to give you the formula. All right? And instead of using xy coordinate this way, you use polar coordinates. It looks like this. Say you have a point, right? Point P. And r is the distance to the origin, and theta is the angle, counterclockwise direction from the x-axis. Okay? So point P here is noted by r and theta. That's what it means. Okay? And you have this formula. And depends on the problem, depends on the nature of the region. R, you can choose the appropriate coordinate system to solve. Of course, they're all going to work. It's just one method is going to be, one way going to be faster than the other. It's going to save you time. That's the thing. Okay. Let me move on to our main lecture today. I'll be talking about triple integral. Okay. So instead of having two integrals, this time we're going to have three integrals. Okay? So instead of having dx, dy, fx, fy, we got f of x, y, and z. Instead of dA, oh, by the way, dA stands for what? Change of area. Okay? Now we got dV. V stands for volume. So it's not a region anymore. It's going to be a box. So I denote it by over a box B. Okay. Same idea, but now it's kind of harder for me to draw because it's going to be 3 dimensions for that box B instead of 2. So let's try the box. Let me try to draw it here. Make it smaller so I have more room. B here. My box. Okay. Okay. You see it's just a box. Looks good, huh? This is my z-axis. It's going to be my y-axis. And this is my x-axis. And again, you imagine the box is in the 3-dimensional space. This box B that we're talking about. Okay. So, if we project the box B right here down to the xy plane, you guys going to see a rectangle down here. I'm not sure. Okay, let me try to project it down. Okay. This is a copy of the bottom of the box down in the xy plane. Okay, you see that? So what do I mean by this? So if you have a triple integral and all x, y, z are constants, and x run from a to b, y from c to d, a, b, c, d, so z from e to f, you have triple integral f of x, y, z, say d, z, dy, dx, and x run from a to b, y from c to d, and f run from a, b, c, d, e, f, okay? And if you project it down here, this is for z, right? So this is what? E to f, and then x is right here. X is from a to b, and then y is right here. Y is from a, b, c, d. See? The box down here, what? For the x, right, it run from, should be a here, close to the origin, right, and b here. Okay. X right here from a to b for x, and for y, run from c to d for y, and z from e to f for z. Okay. And you have triple integral. And this is the nicest KI glimpse, all constant, right? And of course, similar to double integral, you guys can interchange the variable, interchange the integral, and eventually you're going to have the same answer anyway. Okay, and of course, do integrals inside out. So if I write this way, I have to integrate in terms of z first, treat x and y are constant, and after that, integrate in terms of y, and now the z is gone, so treat x as a constant, and then integrate in terms of x. Okay? Now, let me show you a more general case. Imagine that you still have a box, but now the top is not flat anymore, the bottom is not flat anymore. What if you have a curvy box? Okay? So the top is curvy and the bottom is curvy. Okay? And again, the other side for x and y is still constant. So if you project it down, it's still a rectangular shape for the image down here, but the surface on the top, the surface on the bottoms are not flat anymore. So here I'm trying to tell you what the top one is a z2 in terms of x and y. The bottom one right here, z1, is also a function in terms of x and y. Surface functions. project it down to the xy plane, it's still a rectangular shape, constant. Okay, flat here, go down, flat there, go down. This flat go down, this flat go down. Okay. And then with that case, then the integral gonna be like this. Okay. Now I say what? The constant is gonna stay outside. The variable, the function stay inside. So I have f of still x, y, z. I have to put dz, dy, dx in here, and z run from say z1 of xy to z2 of xy. And then integral for y run from c to d, and then integral f run from a to b. For sure that z gotta be inside, but for x and y, still constant, you can interchange the variable for x and y, and the integral for x and y, that's still okay. Okay? Very similar to 2 dimensions, but it's not 3, so it's kind of harder to draw. Okay. Now, what if the y is not that nice anymore? Say you have a curve. And then when you project it down here, and y change to this. There's a curve right here. There's a curve right here, and very similar to the previous case. Now what? Let's call this is y2, right? y2 in the xy plane is a function in terms of x, and this is y1 right here, still a function in terms of x. And as usual, constants stay outside. The most dependent variable going to stay inside. So what do we have in here? Triple integral, right? F of x, y, z, dz, dy, dx. X run from a to b. Y run from y1 to y2. Y1 is above f. Y2 is above f. And z run from z1 to z2, where z1 and z2 is a function in terms of x and y. Okay, and you do the same thing as before. Okay, that's the whole thing pretty much about section 15.6, and I think it's a good time for me to give you guys an example, and hopefully example is going to help you to understand the idea of triple integral. So let me erase some part of it. Okay, how about right here? I actually don't need the picture anymore, so let me erase it. Okay, let me just use the example in the book. I see one. How about this? Evaluate this triple integral. 0 to 1, 0 to 1 minus x, and 0 to 1 minus x minus y, z, dz, dy, dx. Okay? So you see right here, what do they mean by that? This is the function z. Okay? And z is a function in terms of x and y. So run from z1 equal to 0 to z2 equal to 1 minus x minus y. This is z1, this is z2. Okay? And then y is the middle variable. Y1 equal to 0, and then y2 equal to 1 minus x, and then x run from x1 equal to 0 to x2 equal to 1. That's the minimum boundary. Okay, so let's do it from inside out. The integral, the antiderivative of z is 1/2 of z squared. So I know the 1/2 is constant. I'm going to put 1/2 outside. I got 1/2 outside, integral from 0 to 1 for x, integral from 0 to 1 minus x for y, and then I got 1/2 already, so this is z squared. Z run from 0 to 1 minus x minus y, and then I took care of this part inside already. I got dy, dx. Okay, now plug in the upper and lower value for z. I got this is 1/2 outside, integral from 0 to 1, integral from 0 to 1 minus x. Look in z equal to 1 minus x minus y. I got 1 minus x minus y square. Subtract. 0 squared, so 0, and then this is dy dx. Now I'm going to integrate this function right here in terms of y, okay? And I see that this is 1/3 of 1 minus x minus y cubed. In case you don't see it, we do a u sub. U sub is something that we learned in Calc 1, right? So let's do u sub. U equal to 1 minus x minus y. So du is negative dy, or dy is negative du, same thing, all right? And then we got to change the boundary as well. When y equal to 0, y equals 0, then u is equal to 1 minus x, minus 0 is 1 minus x. And then when y equal to 1 minus x, then u is 1 minus x minus 1 minus x is equal to 0. Okay. So really, this integral is going to be equal to 1/2 integral from 0 to 1 integral. Now we change to u, so it's going to be this one going to be u squared. dy now is negative du, and then dx outside, and then u run from where to where? Y is 0, so 1 minus x, and then y is 1 minus u is 0. So it just pretty much changed from 0 to 1 minus to 1 minus to 0, but I got a negative, so we can fix it. We take away that negative for du. We're going to interchange the boundary again back to 0 down here and 1 minus x up here. This is what the problem that you have. Fine, so good. I need some room to write, so let me erase this, right? Okay, so I can integrate the internal integral easily. This is 1/3 of u cubed, right? So I got 1/2 outside, and then I bring the 1/3 outside. Integral from 0 to 1, and u squared 1/3 outside of u cubed. Run from 0 to 1 minus x, and then dx. Now plug it in, u cubed. So to simplify, this is 1/6 first of all. U cubed is 1 minus x cubed. 1 minus x cubed, and then 0 cubed is 0, and then dx. Now integrate it one more time, and I claim that it's very similar to the previous one. Let u equal to 1 minus x. You don't see it, but let me do it quick. It's 1/4. 1 minus x to the 4 with the chain rule, so 1/6. So 1/4. 1 minus x raised to the 4th. This is a negative, so chain rules. Put a negative in here. Run from 0 to 1, and plug it in. 1 right here is 0. 0 right here has become 1 with a negative, so this is positive 1/24. You guys can check it out. Check the algebra out, okay? I'll try to get you an example. I'll do it pretty quick at the end, so skip some calculation, and I'm pretty sure that you guys at Calc 3 level should be able to work it on your own. Of course, if you have any questions, feel free to ask. Okay. So this is a very typical example of triple integrals using rectangular coordinates. Let me move on to the next section, 15.7. I will talk about triple integrals again, but this time I'm going to use different coordinates. Okay, I think they're going to use, let's see, cylindrical or spherical. Cylindrical first. Okay, let's do cylindrical. Talk about cylindrical coordinate. Okay, so this one, whenever you guys deal with the box that looks like this, looks like a can more than a box. Okay, looks like a cylinder. Okay, whenever you have a set, the box B right here is instead of a rectangular shape, you guys have like a column shape like this, cylindrical shape like this. And you should think of the cylindrical coordinate that's going to help you to take care of the problem faster. Okay, so what is cylindrical coordinate? Say you have a point on the x, y, z planes. All right, say point P right here. And you can use 3 components to represent point P in L1. Instead of X, Y, Z, you guys can use R, theta, and Z. And what do we mean by this? Well, Z is the height already, right? So if you project to the XY plane, you have a projection point. This R, this is theta. Okay? So, in terms of X and Y, you use polar coordinate. We need the radius, the distance to the origin, and the angle from the x-axis counterclockwise. You have X and Y. So XY is replaced by R and theta, and of course Z is the height, stay the same Z. Okay? And in a formula for changing is still the same as before. X is R cosine theta, you know this already, and Y is R sine theta, and Z is still Z. So obviously, the X, dy, dz will be changed to R, dr, d theta, and dz. Right, xy becomes R, dr, d theta, you know that's already. And dz is the in dz. Okay? And this is how you have for cylindrical coordinate. So this one, if it's written in cylindrical coordinate, it's going to be triple integral f of R cosine theta, R sine theta, Z, R, dr, d theta, dz, and of course Z still run outside, so say Z1 to Z2, theta run from theta 1 to theta 2, and R run from R1 to R2, depends on problem, what constants stay outside, functions stay inside, like what we had before. Okay? So this is the main idea. And there's a big question that you may ask later on. How do we know which way to change? Again, there's a magic word called Jacobian, I think. Jacobian. It's a matrix, a determinant of the matrix. And you guys can look it up. It's in section 15.9, I say. And hopefully I still remember this at the end of the lecture, and I'll give you this at the end of the lecture. Okay. Pretty much that is. Let me give you an example of triple integral using cylindrical coordinate. All right. We'll look for one. It's 15.7. Okay, we start with rectangular coordinate. Let me just copy this example for the book. Integral of x squared plus y squared dz dy dx, where z run from square root of x squared y squared to 2, and x run from negative square root of 4 minus x squared. So I get this is going to be plus square root of 4 minus x squared. It's a circle. And then x run from negative 2 to positive 2. Okay. How do we understand the problem? And of course, this example, so I'll try to go is as much detail as possible, so you guys can see the whole idea. Let's talk about z. Down here is what? Z1 is equal to square root of x squared plus y squared, right? So z squared is equal to x squared plus y squared. And you know what that is? This is the cone. This is the function of the cone. The cone is something like this. Okay, at the bottom right here. But z is also always positive, so we only have half the cone up here. We have a negative one down here. Okay, this is the cone. And run from where to where? This is the y-axis right here. This is the x-axis right here. And this is the z-axis. Z, okay, this is a cone. It run from that cone, so z equal to this, all the way to z equal to 2. So this plane right here, z equal to 2. Okay? And if you project the whole cone down to the xy plane, I see for sure it's going to be a circle of radius 2. Radius 2 right here. Okay? So, and if I draw the xy plane, this is the x-axis, this is the y-axis. Y run from y equal to negative square root of 4 minus x squared all the way to y2 equal to positive square root of, this is x squared, okay? 4 minus x squared plus or minus. So in the general case, y squared equal to 4 minus x squared, or x squared plus y squared equal to 4, which is a circle of radius 2. Okay, this is x squared plus y squared equal to 4. Circle of radius 2 right here, the bottom, and circle of radius 2. The bottom one right here is y equal to negative square root of 4 minus x squared, and the upper half right here, upper hemisphere right here is what? Y equal to positive square root of 4 minus x squared. That's what I say. From negative to positive, this is lower half. This is the upper half of the circle. Okay. And then x going from negative 2 to positive 2 constant outside. All right. But technically, you guys can use rectangular coordinate dx, dy, dz to solve. But I claim it's going to be better if you convert everything to cylindrical coordinate, and I claim it's going to be faster. Okay, so let's try. Oh, by the way, there was one thing that you guys should see before. X equal to r cosine theta, and y equal to r sine theta. So x squared plus y squared is going to be equal to r squared. Okay, this is how you change it. Okay, so let's work it out. Let me try to redraw the picture so you guys can see the whole thing. Okay, and the projection down here is going to be a circle. Okay. So this integral can be written as what? Triple integral. Okay, x squared plus y squared just r squared dz dy dx. Now, well, just in general, is what? R dr d theta dz. I'm not sure which one is constant, so I'm going to adjust this later. Z is going to run from the z inside, right? Run from, this is x squared plus y squared is r squared squares r. So I better write dz inside. Dz inside run from r to 2. Okay? And then for y, dy dx now becomes a circle down here. It becomes dr d theta, and the radius r is going to be from 0 to 2 for the radius. Okay? And then the angle theta is the whole circle, so 0 to 2 pi. So it's all constant except for the last one, except for r. Awesome. So you see, much easier, right? In terms of boundary right here. And then r cubed, dz, there was another r right here, so let me simplify this a little. Multiply that r, becomes r cubed. Supposed to write another line, but it's a good thing about whiteboard, right? Just erase it, put it there. Okay, so a separable. Remember what we mean by separable? R right here. Oh, but we got the R right there. So we have to leave it down. We cannot interchange the boundary. Let's do one by one. With theta, we can do it. Integral from 0 to 2 pi. Integral from 0 to 2. And here, r cubed dz. So r cubed z run from r to 2 for z, right? And then dr d theta. Okay, so r right here is constant, and z run from 2 to r. So this is r cubed 2 minus r. Right? Z here is 2, and z that was r. And then dr d theta is double integral. Theta run from 0 to 2 pi. This is my 0 up here. And then r run from what to what? From 0 to 2. Now it's separable. We can do it separately. So theta right here from 0 to 2 pi, just 2 pi. And the thing inside, let's say, integral from 0 to 2 pi of d theta times integral from